My name is Colby Nottingham, and I'm here to give a brief introduction to our project Skillset Optimization. It was done in collaboration with AI2 and the University of California, Irvine. So normally in policy optimization, we would be optimizing our policy, perhaps parameterized by a neural network, by increasing the likelihood of actions that led to good trajectories, according to some reward. However, what's very popular now is using language model agents to accomplish various tasks, such as chat tasks, programming, embodied tasks. And a lot of these agents are powered by closed source language models. And so then the problem then arises as to how we optimize a reward signal in a traditional reinforcement learning setup, but when we have a closed source language model that's powering our policy. What is typically done in natural language processing when working with language models is something like in-context learning. If I want to improve my language model's ability to perform a task, I'm going to give it some additional instructions or examples in context to be able to increase its performance. We could do something, there's a pretty naive and easy setup that we could do. We could execute trajectories in our environment. We could find good trajectories and put those examples of good trajectories in our context for our language model. This is like maybe similar to what we're doing in policy optimization, where we're trying to increase the likelihood of good actions or of actions that were done during a good trajectory. However, there's some downsides to this. If we're doing few-shot examples, there are a lot of actions inside of a good trajectory that may be irrelevant and unhelpful. And doing that credit assignment for figuring out which actions are the most helpful is hard to do in context. And secondly, this can result in very long contexts when we're dealing with multi-step tasks. The language model is being prompted multiple times for every single state in action to have a different output, and then putting all of that in context multiple times over to have multiple trajectories in context becomes very long and kind of unwieldy. We propose a different solution than putting entire trajectories into context, and that is putting modular abstract skills in context. So a skill we define as an initial observation and a target observation and a set of instructions from getting from the one to the other. These skills notably are modular in design, such that they're shorter than a full trajectory and can be reused in different tasks. Also, as I mentioned briefly, they are abstract. So in this example, if we have an agent in a text-based game and the agent starts in a specific room and needs to go to another room, we would like the agent to learn that it needs to, prior to actually going from one room to another, it needs to go to the hallway first and then open the door to the target location. And while this may have been experienced in several trajectories with different rooms and starting rooms and target locations, we can create an abstract skill that's more general that can be reused in all sorts of trajectories by substituting the specific locations with some kind of abstract representation like shown here. It's also a lot more concise than a typical trajectory. And these are modular so that they can be composed and used in at one point in time during a trajectory and for a bunch of different tasks, and then also only retrieved when applicable. We use the initial observation in the skill for doing retrieval. So let's look at the setup so far. We have our state coming from our environment. We have a library of skills that we've learned, and then we retrieve those skills using the initial observation, like I mentioned, and then we're going to take that skill target and instruction and put it into the context of our language model to get out an action. Once we get a complete trajectory, we're going to extract skills from that trajectory to add to our skill library. We extract those skills in a few different steps. We're going to look for similar subtrajectories across all of our experience. We're going to look for which of those subtrajectories have a high reward, but without overlapping. And then what we're going to do is we're going to take those similar subtrajectories and prompt a language model to summarize it in natural language into a skill. that is abstract and general and modular, like has the attributes that we talked about. In addition to this, however, we're going to ask for an additional piece of information from our language model agent, and that is what skills it used when executing this action. So we have several skills in context, but we'd also like to be able to further reinforce what's a good skill and what's a bad skill. So we ask the language model what skill it used when performing this action, and then we do what we call skill refinement. And skill refinement is basically that we're going to filter out skills that are used but that fail. So we test this in ScienceWorld, which is a text-based game developed in AI2 where you are in a small home and you're given a tasks such as create sugar water. And then the agent has to go around, grab a container, fill it up with water, put a sugar in it, mix the container in order to finish the task. That's an example task that you might have, but there's a lot of different tasks that are performed. We test across a variety of different tasks and compare to previous state-of-the-art and baselines and get state-of-the-art performance for our model in this task. We also test in NetHack, which is which requires some more spatial awareness, has a lower level action space, and we find in our ablations that the refinement and abstract skills are very important for our method. If you'd like to find out more and to see some more of those results, check out our paper. And thank you all for your time.